So I'd like to welcome you all to this panel, the final panel of our conference. And it's the panel of the AI Day. And so we're extremely fortunate to have 4 wonderful panelists here with us. And the overall aim of the panel is going to be thinking about, I guess, the future of AI in the broader sense. So what is going to be the next big things in AI? And how do we get there? So we're joined by Professor Jay McClelland from Stanford University and also at Google DeepMind. Professor Kim Stachenfeld from Columbia University and Google DeepMind. Ivana Kajic from Google DeepMind. And the odd one out, I guess, Professor Juergen Schmidhuber from KAUST and the Swiss AI Lab.
Well, DeepMind was co-founded by a student from our lab.
And from Google DeepMind. OK, I'm the odd one out. OK. So we just, of course, heard from Juergen about his sort of future predictions for what AI is going to look like over the next, well, just 14 years. I thought we'd just go very briefly, one by one, maybe skipping out Juergen, in fact, we just heard from you, from Jay down to Kim and Ivana, of what your, well, actually tell us a little, in fact, we will include you, Juergen. Just tell ourselves a little bit more about yourself and what your overall sort of research thesis at the moment is. And let's try to keep it just about a minute. Starting with Jay.
Well, I'm still trying to understand the human mind myself. That's my fundamental aspiration. It's been that way for a long time. I've been puzzled about my own successes and failures of being able to understand things and wondering why I did what I did and why I didn't do what I didn't do and why I continue to do what I do and think about other people in the world around me in that way. And yeah, so I'm not so much able to speculate about the future of AI because I'm more deeply immersed in thinking about the future of our own efforts to understand ourselves. So I'll pass the baton with that.
I'll push back on that later. But
okay.
So I'm Kim Stachenfeld. So right now I'm doing a lot of AI for neuroscience in 2 different ways. One is AI tools for neuroscience. That's what I talked about yesterday. Basically, like, can we use the ability of AI models to search over very large model spaces in order to come up with descriptions of the patterns we're seeing in human and animal behavior. My background in neuroscience, the kind of neuroscience work I did before, was also AI in neuroscience or machine learning in neuroscience, but it was more, here's a machine learning algorithm that works pretty well, that does something interesting, that seems to represent a compelling hypothesis about computation in the brain. Is this a good description of what's going on in the brain? And I still do a lot of that kind of work, but they're both like really fundamentally different, but interesting ways that AI and neuroscience interact together. In the previous phase of research I was doing some work that was AI for physics. It was just basically like not anything to do with neuroscience at all. It was really pure AI problems, and we happened to be applying them to benchmarks in physics. I've now shifted almost entirely to doing work that is aimed at neuroscience, is trying to understand the brain, not necessarily develop new AI methods as the primary goal, just because I think it's a pretty fun time to be applying AI tools to neuroscience data. I think there's like a lot of low-hanging fruit there. In a lot of ways, AI is like, there's a lot going on. It's clearly an exciting time, but it's also very crowded, and it's kind of exciting to be on the side of taking AI tools and playing around in neuroscience with them.
So my name is Ivana, and somewhat similar to Jay, I also got interested in human mind. And the way it started is that during my undergrad, I was working on initial artificial intelligence. Machine learning was kind of growing, but still not as big as obviously today. And I thought to myself, well, artificial intelligence is really very interesting, but like, what about intelligence? How about learning about humans? And so as a computer scientist, I didn't have a background or even opportunities to study human mind or animal behavior or neuroscience, and what that led me to pursue a degree in computational neuroscience. So for my master's, that got me exposed to a little bit more about how the human brain works, but also what kind of computations underlie the cognition. And that proved to be a very useful toolkit also to understand human mind, but also at different levels. So starting from low-level neuronal activity, which is actually important in understanding diseases. It's important understanding lots of different behaviors up to everyday behavior. So how do we learn? How do we interact with others? What determines our social behaviors? So all of those things can be also studied at that level. And then in my PhD, I pursued that further, also keeping this track of trying to be close to kind of how human minds work and understand them, which ultimately led me now to where I am, which is doing research currently on multimodal models, so models that can process vision and language. And I think as they're getting more and more capable, we are finding more and more utility from the methods that we have developed in cognitive science, in psychology, et cetera, to try to characterize and study the behavior of these models.
Okay, yeah, again, why not? Yeah, you can tell us a bit more about yourself as well. And why do you care about AI and what you're currently focused on?
My name is Juergen, and since my teenager times, I've been trying to build a learning AI that learns to become smarter than myself, such that I can retire. Unfortunately, they keep increasing the retirement age all the time.
And what's your
What's your estimate?
while you're still not retired?
There was something else to the question?
Yes, while you're still not retired, yeah, what's your the current thing you're working on?
Yeah, I'm still trying to solve the same old problem, and during some of you maybe have seen the talk, we are still trying to build AIs that have this world model that they use to plan, and they have artificial curiosity that they need to train the world model in a very focused and selected way, rather than downloading the web. And we are making progress on all fronts, but we are not there yet because, also because current hardware is still wanting.
Me? As you can see, we've got a diverse set of people, diverse set of interests and approaches, and looking forward to the lively debate that they will produce. So, as we said, the overall ambition of this panel is to be thinking out what is the next big things in AI and how do we get there. As we said, we heard from Juergen in his talk what the future may look like, but maybe less precisely about what we need to solve in order to get there. And so I was wondering again if we just go down the line from Jay onwards, sort of what is this next big thing and how do we get there in a few minutes?
Well, I think that the learning efficiency gap between brains and models is a very clear marker to me of a place where we need to be thinking hard and where there might be some low-hanging fruit. Like Professor Moss, I've recently been fascinated by behavioral timescale plasticity, which some of you may have heard of if you heard his talk, which is something we've learned about the learning mechanisms and use in the brain that actually, opened up the space for thinking about how the brain solves some of these problems that we didn't have before as part of our toolkit. And so what I'm guessing is that will be a very fertile ground for exploration over the next few years. But more generally, I feel like there must be more things like that we, don't know, that we haven't anticipated, that are going to come into the picture. Maybe somebody did anticipate it in 1991. I'm not sure or not. But, that it'll suddenly become, well, the scale of the computing will be ready for it, right? I think that was what happened,
yeah.
Right? Like he's right. Paul Werbos did, develop backprop before Rummel Harden. He tried to apply it to neural networks, and people at MIT, wouldn't give him the time of day. And So he ended up being a program officer in NSF instead of developing neural networks.
But of course, it was even much further. Much earlier, 1970. Serpolin Einma published the whole
I
thing.
don't know. I wasn't able to understand that paper, so I'm not as familiar with that work, but I've heard about it as well. So anyway, all good ideas are discovered many times. All of Juergen's ideas about the future of robots taking over the world were anticipated by Olaf Stapleton in his...
Olaf Stapleton, yeah. Except that, let's not go into the details, but you are right, So humanity collectively has seen this coming, And in the 1800s, 1816, there was already a novel by Hoffmann, which was exactly like Ex Machina. Have you seen Ex Machina?
Yeah, Ex Machina is another...
which is a recent movie, 200 years after the same story was published.
So we can all imagine these futures in which the robots have taken over from us. Whether they'll actually come to pass.
Great. How do we get there?
We're not necessarily hoping for that.
I really hope the robots don't take over, just so that my controversial opinion on that is known. I mean, the stuff that I've been thinking about the most lately has been AI for science, AI for neuroscience, because that's really directly related to the research I've been doing. I think the big question that I get whenever I give a talk on Cog Fun Search, and it's just something that's come up a lot in this meeting, is to what extent are models going to be able to come up with qualitatively new ideas? Like the fact that we got programs here is very clearly informed by just the giant literature on RL algorithms that already exists. It grabs, mixes and matches snippets. The fact that it can mix and match lots of snippets is very good for exploring a gigantic and somewhat comprehensible model space. I think the power of that's going to give us a lot. But how are we going to do when you want to try to model really new behaviors, model really new phenomena? That's an out-of-distribution problem. That's a generalization problem. How are these models going to do? Can we really mix and match and get nice compositionality the way humans seem to be able to deploy in select settings? So that is a big problem and something that models have gotten a lot better at, and maybe they'll be perfect for our use cases here. Maybe there'll still be room for improvement. I think we'll have to find out. The other thing in the AI for science realm is that the current bottleneck to me seems to be, at least in these neuroscience domains, that running experiments is hard and takes a long time. Good experimental, we can't get away from, at least as far as I can see, actually testing things in the real world. We need experiments. So we can't just say AI is going to solve all science and we're not going to need to run experiments in order to make scientific insights. If we can accelerate experiments, if we can suggest good ideas for experiments, that would be something that would be really profoundly helpful for driving the pace of discovery. And I don't think this is I don't think we can, pause that kind of scientific investigation and hope AI can figure it out from the place we're currently at. Yeah.
Thank you.
Right, so I have to say that I agree with many statements that have been echoed here, and especially with Juergen's view that we need things that act and learn by acting, learning from the environment, and don't rely on just this passive, perhaps, ingestion of the data. And there, one maybe barrier, one thing where I see we can still make a lot of progress is improved sensory processing. And we see that in human sensory perception and processing that we are actually efficient at what kind of information we are selecting from the environment. When we move around, how do we pay attention to, what do we pay attention, how we disregard things that are perhaps less important. I do remember how to navigate to Diocletian's palace in Split, but I might have forgotten what I have eaten for breakfast 2-3 days ago, right? But the fact that I've been going there every day for the last few days means I'm building this map in my head and similar. So I think learning from data in an efficient way and knowing what to learn, knowing what do I not know, where do I need to improve, all these mechanisms perhaps we take for granted when we observe them in ourselves, but they're not as intuitive in AI systems. And I think in order to get there, we might need to revisit or question some of the assumptions that we make, such that we have pre-training and post-training. We have these very rigid paradigms that we don't observe perhaps in our environments. We don't necessarily differentiate as strictly between these different regimes. It's all continuous. Everything is happening real time. We are revising our actions as the evidence comes in. The assumptions about learning in batches, learning with many, many types of data. Sometimes we have just one sample, et cetera. So I think those perhaps will be things that we might think about as we're moving more and more towards the AI that is interacting with the world.
Thank you. And Juergen?
I totally agree, of course, and I think we are going to see more and more devices and AIs that are not downloading the web, but instead in a very focused way, executing their own experiments to see what happens if I do that, and if I maybe spill some water and whatever. So very dedicated and focused ways of collecting data that is of interest to those who don't know yet the physics of the world and how the world reacts to the actions, and then over time, the intrinsic joy that we get from learning what's going on here goes away because we understand what's going on, and this intrinsic reward is fleeting, it's ephemeral, it goes away as we are understanding this part of the world, and we are motivated to explore another part of the world that we don't understand yet. And every little baby is a scientist, and it's conducting its little self-invented experiments, and it just moves the hands like that. It doesn't even know that it has hands, but it sees, oh, my video is changing, and it learns to predict the video. And that's a very cheap experiment, and 20 years later, the same baby is a scientist at CERN, and it's still doing the same thing, except that the experiments are now much more expensive and costs $5 billion to find the boson, you know. And in principle, all the same thing. And we just need to implement that in our robots on hardware that doesn't destroy itself all the time. Yeah.
So I want to complement what you guys have been saying with another element. I don't want to say I'm disagreeing with the importance of that sensory, physical embodiment and the opportunity for self-directed exploration. But I have been very struck by the way in which we socialize each other and structure our experience, our construals of the world, and the concepts and frameworks within which we arise and develop. And I'm going to use Mozart as my example here to make this point. So Mozart probably did have some genetic advantages relative to other people, but his ability to compose the music that he composed, starting at the age at which he began to compose it, was dramatically affected by the particular time and situation into which he was born. You know, his father and mother were both musicians. His older sister was already there. He was born to be the fourth person in the family string quartet. And he was completely surrounded by a culture of music at a particular moment when the affordances of developing further the sort of compositional styles of the emerging classical music framework were latent and ready to be exploited, right? And he came into the world at that perfect moment, into a culture that had provided all of the resources on which that kind of explosive contribution could arise. And I just think that, you know, all of this evolution that happened in that last 13,000 years that you were mentioning, or the last 13 years that you were mentioning, is all sort of part of that process, of that, whatever that cultural structure is, that some of us are so lucky to be born into at these wonderful moments in history, and it's not just the affordances that the young self-directed infant brings, but also all of those experiential constructs that shape them, those opportunities.
Absolutely. Yes, it depends on where you are living and what opportunities you get. And this guy over there in this particular country has no connections to music or to books or to computers, although he might be the most brilliant scientist ever, but he has no chance of unfolding his talent. Yeah, absolutely. So all of civilization is collectively evolving in a rapid way, much more rapidly than biological evolution before that, where you can very quickly exchange ideas in a way that allows this evolution of ideas, which are also competing with each other, and Reformation is competing with Marxism, and this scientific theory is competing with this one, and within a few years, not millions of years, but years, some of them win, and others get discarded, and so on. And so you have this rapid technological evolution, which is often concentrated in certain places, like in the 1600s in the Netherlands, where suddenly you had a lot of money coming in through the East Indian Company, and suddenly there was money for inventing the stock market and having people like Huygens develop lenses and making breakthroughs in optics, and at the same time enough money to finance all these revolutionary artists like Rembrandt and Vermeer and so on. So we always had these hotspots which were driven also by money, by funding, and the richest places usually are those that then have a higher density of these hotspots, and it's part of a complicated, but in principle simple thing. As you have more resources concentrated in a certain area, and you have shorter communication paths between these individuals living in these areas, you are just accelerating scientific progress and progress in the arts and in music, which is all driven by the same principles.
Thank you both. And so, just so I can understand all of this, were you guys both making analogies between these social structures and what we should be doing in AI, or commenting on it's a necessary component for us to be doing as a society ourselves? Like, where were you thinking of that places in the next few years of AI development?
Well, I do think that it's not lost on people in AI. The part of the success of the OpenAI models was due to their extensive use of code in training the models, for example. This is something that has widely been talked about. And code is, of course, something that was invented by humans, right? The idea that we could write sets of instructions to carry out sequences of operations that would exactly reproduce an algorithm of some kind and so on is a human constructed sort of thing, and it becomes a technology which we can internalize and structure our own thinking with, and it's been heavily influential in successfully training the models of today. And so, I think that it's going to continue to be like that. And I guess I also think it's always like a complicated and condition, right? So that's that and some architectural breakthroughs that are needed or advances over the current way of doing computation in LLMs and so on that will synergize together to make interesting future progress. But that structuring that the data provides, and it's of course not just the code in the data, it's also the systematic arguments that are laid out in the mathematics textbooks that are in the data, and all of that other stuff that is contributing to the structuring of the abilities of the models that we even have now to be, simulating successful thinking as well as they do.
Yeah, but do we as AI scientists want to be constructing those environments for the AIs themselves, i.e. encouraging them to operate in these very social conditions, and therefore do we have to solve problems such as multi-agency and so on, or do we just train things like LLMs and stitch them together? I mean, is there these fundamental problems that need to solve at the multi-agent level in order to get those vast increases in technology that you were describing that came about from the social structures in humanity? Open to anybody as well.
I'll let somebody else respond.
If I can, just to add, I think we are all here qualified to give comments on the technical advancements and what we think needs to change in those terms. But there are also societal advancements that I think need to happen, and especially how does AI interface with wider society if we want to make it widely useful. So for example, we want to deploy an AI system to be helpful to doctors. So when they are diagnosing a patient, they can do that more efficiently than they would do when they work by themselves. Is that technology built in a way that makes it very easy for them to use it? That makes it easy to detect these cases? How does that communication happen? And who should be doing that as well? I think this is something where we'll also have to see ongoing research and progress to maximize the utility of such systems.
But it's happening as we speak because there's all this competition in the market and all these companies, they want to sell you something, maybe a little cancer detection device, where you then take a photo and it's easy to use because otherwise you wouldn't buy it. And so different companies are offering devices like that. And through the struggle, the evolution of the markets, all these players in the markets, they are part of this evolutionary process, which is guided by financial incentives, driven by the customer who buys only certain things and ignores other things. It's already happening as we speak. Yeah? So you could even argue that in a laissez-faire economy, it's all going to happen automatically just for commercial reasons.
Okay.
I think that's the...
Go ahead, Kim.
I mean, so my sister runs a startup, so she's in the business world, and I was talking to her about about this, about like how far about whether all research could happen in industry versus academia. I'm in both. I see a lot of advantages to both, and she pointed out, like monetizing something is really not trivial, even if it does provide a service to a lot of people. It might not provide a service to people who have a lot of money. It might not provide a service on some time scale. There's a bunch of reasons. It might not provide a service. It might be something that's like an interesting investigation, but is down the road from a product. So I mean, I'm at Google DeepMind. I think the stuff we do is awesome, and I don't think that everything will be free market driven. I'm not sure if you do either, or you're just kind of saying that as a...
So the universities are also part of this evolution,
of course, yeah.
And then there's this taxpayer, which is financing the universities. Yeah. And in some countries that works really well, And in our field of deep learning, so 99% of all the basic algorithms were not invented at the big companies or at the famous companies. No, they were invented in small academic labs with not so much funding, where the funding was measured in hundreds of thousands, not in hundreds of billions. And the thing that happened in the big companies is scale that up, and because they know how to do business, they know how to attract investors and give me 10 billion here and 10 billion here, and I can buy a lot of compute, I can take the existing algorithms and add a few epsilons and make them faster and scale that up, hire a couple of really good engineers to implement that in AI data centers and so on. All the stuff that academia cannot do, that's what the companies do. Oh, that's good. So, and why do the companies do that? Because they want to sell you something, and they hope they will have a good business model. At the moment, it's interestingly happening as we speak because it's not clear whether the big companies really have a good business model. Because if the president of a famous country stands up and says, we are going to invest 500 billion into AI data centers, remember that every 5 years, computers getting 10 times cheaper, which means that within the next 5 years, some investor is going to lose 450 billion. You know? And this means you need a really good business model to recuperate that loss. And it's not clear whether anybody has that because, you know, you have all these incumbents and the new startups and they're using open source code. The open source code is maybe just 8 months behind the best models of the well-funded big labs and so on. So actually, in many ways, all the current trends are playing in favor of the little guy, of the little customer, and not really in they are not really so beneficial for the big companies. You know, there was a time when Google and Microsoft, they were really nimble software companies, and you know, they had a small team of developers improving a shitty operating system a little bit, and then rolling it out to to a billion people using all their own computers to run it, you know. And now suddenly they are investing into AI data centers in the cloud, and they are thinking about how do I get the electricity for all these, and I have to now buy nuclear power companies and all kinds of things. They are becoming like utilities, you know, like electricity companies, and it's not clear that they are going to remain as profitable as they are at the moment. So lots of evolutionary pressures still not fully understood at work as we speak to see who is going to profit in the end and who is going to go the way of the electricity companies.
It's very interesting. It's very interesting commentary at the high level of AI and the future of AI and tech there. I thought I should also say that at this point, feel free to interrupt each other, interrupt me, run an ad lib, do what you want. But I thought I might bring things back to a little bit lower level. In fact, it was something that was mentioned by several of the panelists. And that was about these agents will have to go out into the real world. They have to experience things. Maybe they need to be in robotics. But they're not going to be operating or in the same way in which these models are currently trained. So for these language models, of course, trained on all of the internet. And then they've got some some RL based on some very verifiable problems, such as math problems or coding problems, or things where there's a definitive yes or no answer. But at some point, these models are going to have to learn a little bit like humans in this fuzzy world, where it's not sure what is right and wrong. And you have to learn from real experience, not this very curated experience. So we sort of heard one way about doing that, and that's from these intrinsic rewards, which may be from exploration. But I was actually wondering, as a question to Jay, of whether there's things that we can take from cognitive science, or what might be the appropriate reward function of humanity that we can train these models with, or any ideas about that?
Okay, so I'm not going to answer that question first. I'm going to answer a different one, which...
But you will answer it last.
Well, okay, I'll try. But the thing that I found myself thinking as you were starting to talk was this robot that we imagine being, you know, sort of like a human child would actually, of course, have internet download capabilities and be able to be in communication through sort of parallel mind with every other one of these robots. And they wouldn't in any way, you know, just be little replicas of the human being. That would be, you know, you could build them like that, but why? I mean, that wouldn't necessarily be the mode, right? And even in like in self-driving cars, you know, for many years, the first time I heard somebody talk about self-driving cars, they were actually talking about a network of self-driving cars that were all in communication with each other, as though they were a single intelligence that could, you know, allocate resources to driving people in different parts of the city in this sort of parallel way, as opposed to being like us, limited autonomous entities. And so I think that, you know, we shouldn't take for granted that we're going to have to, and you know, at the inception of this new little tiny robot, well, it probably isn't going to like grow up from a baby in the biological way, right? And of course, it could be instantiated already with huge amounts of prior knowledge and et cetera. So I think that the scope and scale of the possibilities that will become available when we start actually having robots is going to be very, very different from just thinking of them as being like replicas of ourselves.
And that's the reason why the next epoch is going to take only 13 years and not 13,000 years.
Well, I don't know about that. Interesting.
Once you have taught...
Shouldn't it be like 13 months or something like that? Or even 13 seconds? I mean, after a couple more iterations of this...
9 months?
If you divide the 13 years again by 1,000, you come out with about 5 minutes.
Yeah.
In the last 5 minutes, really exciting things are going to happen.
Yeah, so it'll all be over before anybody here is 20 more years older.
But I completely agree. So of course, so at the moment, the thing goes like that. You have a baby, and then it takes 20 years to train it, to do all the things you need to be a valuable member of society. And of course, once you have a robot in the same state, you can copy it like this. And then you have 1 million of them. And each of them will soon have slightly different experiences because they will be in different parts of the world and so on. And occasionally they can merge or do whatever with these different experiences. And that's the reason why everything is going to be 1 million times faster than what we know from biological evolution, which was pretty slow, and now technological evolution, which is much faster than biological evolution. But this new kind of evolution, which is ahead of us, it will be crazy fast.
I mean, so if we're not growing them up like kids, which I understand we can't treat them as little humans, then what do we treat them as, and what is the mechanism by which we train them to get to what sort of things that Juergen and Jay are talking about?
Maybe we should throw it open to the audience now. But I don't know. Other people may have things to say about that. Don't want to cut off the other panelists.
So I get, our current learning paradigms going to work for distributed computation. We can turn your learning of these vast networks of three fundamentally new classes. Any insights on that?
Fundamentally new tasks?
Do we need fundamentally new classes of learning algorithms? Or are the things going to be sort of effectively bootstrapped from what we have now?
Well, as I was trying to say before about like this, I am guessing that there will be big changes in the way we think about that in the future. This idea of this sort of like these orders of magnitude telescoping down has obviously got to give out at some point. It's some slightly different regime. Feels like it must happen at some point. I don't quite understand what it'll be like, of course. And the only thing that I know for sure that I can't predict is the future. So, how could I speculate at all about that? But it just like the fact that, it becomes apparent that some other approach is better. Maybe it is a factor of scale. The computing scale was presumably necessary for, the setting of the moment when people started having this sort of feeling that they could figure out how to train multi-layer neural networks, right? And so as that scale changes, these other ideas will emerge, and they will be different. And, we're still in a world where people can talk about neurosymbolic computation as though it really makes sense to have the explicit symbolic engine complementing the neuro part that does the fuzzy stuff, rather than what I guess I deeply believe that it's all kind of like ultimately emergent, and it's just like there's some sort of scale or algorithmic structuring or learning algorithm related or some set of things of that kind that will put us in a place where we'll see that makes sense. You guys will still be here. but maybe I won't. I don't know.
So then, what if you're suggesting there will be these new classes? So I guess the question I'm interested in now is what that we know now will be part of the final answer, and what won't be?
So, of course, we are going to keep all the brilliant inventions that work so well, like, for example, pocket calculators and no large language model of the future that is reasonably intelligent will throw away the opportunity of using a pocket calculator for doing something much faster than what you could do through this super expensive large language model. So, of course, you will have all kinds of symbolic calculator-like things and theorem provers who do something that's really different from the large language models, except that the large language models and similar devices are going to cut the search trees using lots of experience with different proofs and so on. But of course, there will be lots of great algorithms that are symbolic, according to what most people would qualify as symbolic, which are going to be used. Like, what is the shortest path from A to B? Well, you use Dijkstra's algorithm, and it's not going to change. And the large language models are going to use the same thing, because it's so efficient and cheap. So you use it whenever you can. So intelligence, the hallmark of intelligence is be lazy. Try to do something with the least possible effort, computationally, energetically, and so on. So any intelligent being will try to minimize the efforts for achieving any solution to a given problem. And so if the problem is about multiplying numbers, you use the calculator.
And then what about things at the level of, I guess, what people would think about modern AI, and they're sort of going to constrain their thoughts in neural networks? So what aspects of them need to change? Like, are we thinking that, in 10 years' time, part of the answer will be transformers, part will be CompNets, part will be RNNs? Is there some new thing that needs to happen? Which parts won't we keep and which parts we will? Is it the learning algorithm? What are your thoughts there?
Well, I think you're actually pointing out an important bottleneck, which is that we still don't have a great single unifying model that is as capable of processing text, image, but then all the other signals which we have in the environment, such as auditory signals, haptic signals, etc. So our experience is highly multimodal, and our current models are not. And so how do we combine all this information to get the abstractions, to get world models? I don't think we quite know the answer to that yet. We are working on this. And as I was showing earlier, when it comes to number understanding, generally we do see that text-based models will perform better. And then as we start adding vision and as we move to generating images, we see this sort of degradation in performance. So we are not forming, we don't see the models form this idea of, let's say, a number that's invariant, that's context independent. And I think it will be a question to see how do we get to such behaviors that are perhaps less context dependent and more robust, and what it takes to get there, what exactly kind of architectures. And maybe we are on the way there, but so far it seems we can still find those cases where that's not the case.
One other, I think that makes a lot of sense in trying to get multimodal architectures that that behave at scale, that can find cool abstractions. It's going to be an important ingredient. One other ingredient that I don't think will be controversial, but maybe hasn't come up, is we talked about learning on different timescales, and memory on different timescales also seems like an ingredient that will be really useful for some of the problems that are still open. I worked on a RAG team for a little bit, a retrieval augmented generation team, and that overall, that made me very bullish on the potential of having the ability to do rapid episodic-like memory and have that inform a generally statistical learner. So I don't know what architectures we'll be having in the end, but I think things that can mix this kind of slower statistical learning, this more rapid in context learning, that can compress in context learning by having access to an episodic buffer that can inform it dynamically. That seems like it is a core part of human memory, of course, and then it also seems like something that will be generally useful. I also think just it's going to be very immediately useful to the next state of AI, although not really like generally in the practice of making predictions about where AI is going. And the reason for that is just the LLMs are very big. It takes a long time to train them. It's very expensive to train them. Not everybody can do that. And if you want to take a model and then adapt it to a particular function, you're not going to just train your own LLM on your new data set, mix in your data to a giant corpus. You'll take an existing one and then try to augment it, either by putting personalized or specialized information in a buffer or fine-tuning. So I think those kind of things that take a model and make it adapt to something will be useful for getting models that work in the real world that'll get them for working for these like more specialized applications too.
And Jay, you touched on in your talk, of course, there was a lot about transformers and what they can and can't do. And you were suggesting that new architectures will be required to solve these sort of, for example, the reversal curse. Are you still thinking things analogous to key value is going to be an important part of the picture, or whether there's something different? I guess it relates a little bit to your timescales, being that's a fast timescale, slow timescales.
I do think about that a lot, and I think as one of the things I have shared with a few people and I thought about including in my talk was, the notion that at least from the point of view of understanding human thought and the way we're able to maybe be more efficient learners than today's machines, it does involve an idea that we have some sort of way of sort of unitizing sets of things that fit together in a way that is roughly equivalent to the way sentences work. Like, for example, we could say something like, John gave the book to Mary, and it's expressing a relationship between a small number of entities, and those are the kinds of things that we share with each other when we state sentences. And, we can also understand complex mathematical ideas at the same level. It's just that the things that go into them are, constructs that themselves are fairly complicated, but they get related to each other in a way that we can then communicate about them and encapsulate them in our mind and use them as guides for our thought. And I think that, when I think about, for example, episodic memory and things like that, I think, we have actual evidence from cognitive neuroscience experiments that, at the end of a chunk, like an episode-like chunk of a little vignette or movie or something, there's a big moment of functional connectivity between the hippocampus and some cortical areas that seem to be representing the sort of the moment at which you sort of store your compressed representation of this event that occurred. And these things are not happening in our language models today. They're, they just got all these tokens all spread out in the context. We tried to figure out where in there that relationship between John and Bill, is. And it's really hard to find. And I just feel like somehow we'll understand more about that maybe sometime in the next 5 or 10 years. And that's one of the problems I myself am actually working on now.
Okay, well, we're going to turn it around questions to the audience in 1 second. Well, not quite 1 second, in one moment. But I wanted to have a final question. In fact, maybe even in this, when you're answering it, you'll address some of the points that Jay was just talking about. But the question is going to go to Kim and then to Juergen as well. And that is because we're wanting to give this question to both a neuroscientist and I guess Juergen hasn't interacted too much or done any neuroscience before. So the question is, in getting to this answer, whatever it might be, or on that journey, or even thinking about the sort of things that Jay was talking about, is will neuroscience be relevant to that? Will neuroscience have a say in that? Will it be able to direct it, or will it effectively not be relevant? First for Kim, and then for Juergen.
Are you sure you don't want Juergen to go first? I mean, okay, yeah. I mean, I think so. I mean, I think for at least for the very basic reason that neuroscientists and machine learning researchers are thinking about problems that have a ton of conceptual overlap, and the time that one field spends thinking about it can be amortized, and if the fields talk to each other, we'll have thought more total thoughts and have exchanged some interesting and good ideas. There's obvious limitations to the idea of like, oh, maybe this is a good idea for AI. Let's do an experiment and see if it's in the brain. Because experiments can take a really long time, and trying an idea sometimes doesn't take a long time. You can just code it up and try it. But I still think like looking at how the brain does something, it doesn't always take a long time if you're looking at behavior, and it also can be really informative because we think generally brains are pretty robust. Brains are inside of organisms that have dealt with a big natural variety of problems. The brain's solution to problems is going to be something that has stood up to a reasonable amount of robustness. So I think understanding what's going on in the brain is a useful reference point for understanding something about our algorithms. And then exchanging ideas between the fields to me seems to me like it's very useful. I'm not a historian. I think it's been useful historically, is my sense, but I'm like not gonna. I'm not a historian. Yeah. So I guess that's sort of my sense. I will say, like right now, especially these questions like what's gonna. What do we need now to go forward? I don't feel like I have a super clear sense of that, just because I don't totally know where we're at right now. I feel like we're kind of. Maybe I am just kind of catching up, but it seems like generally like we're still evaluating lots of things and seeing what can happen. And if we run some kind of experiment with LLMs, we're not always sure how it's going to turn out. So it seems like we are still investigating a lot of things, and exactly what we'll need will depend on to what extent we're already plateauing. So new ideas, whether they come from neuroscience or anywhere else, are going to be informed by what we're doing well and what we aren't.
Okay, thank you. So Juergen.
There are quite a few neuroscientists in search of funding running around and claiming that their research will help to improve AI. And I don't buy that. The last time that neuroscience contributed anything to AI was about 60 years ago, people like Hubel and Wiesel saw something that then the computer scientists, Fukushima basically, used to create these convolutional neural network architectures. And at the same time, the spiking neurons, you guys probably know better who discovered those. And they are still relevant when you think about energy efficient computation, so it's still inspiration from that. But in many ways, it seems to me that a neuroscientist who is trying to contribute something to AI, that's a little bit like an electrician from the 19th century when they already knew about electricity, and now you give him a complicated modern device like a smartphone, and now his goal is to understand this smartphone, just like the neuroscientist tries to understand the brain. And so what does he do? Well, he pokes around a little bit, and then he realizes, oh, if I press some of these buttons, then inside there is something that's getting warmer over time, and I can maybe construct a heat map, and some of these trillions or billions of little things, let's call them transistors. They heat up in a way that is related to what I'm doing. For example, when I'm speaking to it, another part of the let's call it chip, heats up, and then you get a vague idea that something is happening, but you have no idea what's really happening. And then he says, okay, let's maybe take a needle and poke it into the chip, and then let's try to hit one of these little transistors, okay? And then you hit one of the little transistors, and you inject maybe some currents, and sometimes you suddenly get measurements, and then it turns out there are these characteristic curves of the transistors, and some of them go like this, and others go maybe like this, and others go like this, and so on. And he thinks he is now onto something, But of course, all these transistors have only one purpose, namely to switch between 0 and 1. And what is the smartphone currently doing? It's sorting addresses, and it's using quicksort, and you can write down the code of quicksort within 3 lines of code, recursive code. And then the true intelligence of the smartphone is this: to understand that, you have to understand the 3 lines of code. And he has no idea how to get there. He's really disconnected from the true intelligence of the smartphone. And so he is overwhelmed by all the little details he can find in the smartphone, which are totally distractive. And
I'm going to take that as an answer of no.
So you get the message.
And give Jay an opportunity to respond.
Can I ask a question?
Oh, wait. He's stacking the deck here, so it's not really fair. But go ahead.
Yeah, I don't know. This is a very bold move. I'm going to contradict Juergen. Well, not quite contradict, but I would like to perhaps argument another example. You pointed out Fukushima as an example where we have taken something from neuroscience, inspired our architectures to create connets that were immensely popular. One niche field where it seems like we can still learn a lot from the brain and biological systems is happening in the space of neuromorphic hardware. That's a smaller community, but there has been work of Misha Machovald and Toby Delbruck that you might be aware of.
Oh yeah, I know them. Yeah.
And of course, and so there by carefully studying human retina and how we perceive the lights, they have developed spike-based, event-based cameras that are way more efficient at processing visual signals than the classic frame-based systems. Where they're useful is probably, their usefulness is perhaps restricted in certain cases. For example, they are better at night. They can record events that we wouldn't be able to see with more conventional cameras. But I think there are these perhaps rare gems or examples where we have seen use cases. And perhaps if we search more, we will see more as well.
Yeah. No, I completely agree. So 20 years ago, I used these cameras of Toby and his team, and we used it for making a robot that can balance a pencil, which is not so easy. So a really fast camera used then for a robot that learns to do
20 seconds.
What is it?
20 seconds.
Oh, I have a 20-second limit now.
Yeah.
Okay.
You've got to be fast like these cameras.
Nevertheless, so the basic principles there that are being used in this camera, that is the stuff that was discovered in the 60s by, a Japanese name, Nagumo Fitz or something like that. And so these spiking neurons, which are really good at doing these things, and predictive coding, but these are all really old concepts. So last time neuroscience contributed something useful to AI was about 60 years ago.
Okay, so were there responses from either of you two?
Well, I did want to say, you might not disagree with this, I don't think. One of the things that the hardware of the brain offers that the current hardware doesn't is the actual parallel physical connectivity that neurons can really have in the brain, which is not something that we have in silico, right? We have 3 layers in silico. In the physical brain, the wires all interdigitate with each other in such a way that the actual connectivity possibilities are vastly superior. And I think that is one of the architectural differences that, maybe someday there will be some organically growable sort of, neuron-like sort of stuff that could be completely synthetic. I've been imagining that since I first had this thought about 40 years ago.
Yeah, exactly, 40 years ago. Because, and back then, so why are the brains wired the way they are? Why do we have this 3-dimensional volume where you have lots of little processors and they are connected through lots of short cables and few long cables, such that you still can quickly go from A to B, but you minimize communication costs because you have lots of short cables. And so if you look at the old supercomputers from the 60s, the old Cray machines, they are exactly like that, lots of short cables, few long cables, because this is dictated by physics, by the 3D nature of physics, and it's not really, and we are not really trying to imitate the brain. No, in our modern chips or the chips that are going to come, which don't work well, but they are driven by engineering and mathematical and first principles, and not really by the desire to imitate the brain. No, we just have to deal with the 3D world. And of course, we don't want to do the thing that NVIDIA is now doing, have all these flat chips. No, you want to go 3D, and you want to connect through short connections, the different chips, the layers, maybe through light connections.
Cool the way the brain actually doesn't have to do any of that stuff? I mean, it's a different kind of blueprint, right? And I think that's going to be really something that's going to be very exciting to see how that could unfold in synthetic architectures that we could develop.
So the brain's got extremely good essentially on-chip memory, which
Yeah.
But so the brain has all these constraints, right? And so it has only very limited chemical materials that it can use to build cables. Cables are really slow, much slower than the copper cables, because it doesn't know where to get copper and so on. So it's super limited, and we are going to greatly surpass all of that and still, follow the same principles dictated by physics. Lots of processors, small volume, lots of short connections, few long connections.
Thank you very much for all of your questions, for all of the panelists, for the wonderful discussion. So let's give them a big round of applause.